Good morning, good morning. Welcome back. I'll check your homework in a little bit if I didn't get to it yet. We'll take our quick look at the calendar. The last two classes we have focused on exponents, lots and lots of properties of exponents and how do you work with exponents and how do you simplify things with exponents. Today it seems like we're shifting gears as we talk about roots like square roots and other kinds of roots and radicals. But it turns out these are still related to exponents. So it's all going to come back together to exponent stuff. And just in terms of looking ahead, a quick heads up, Friday is a normal day, Monday is a normal day, Tuesday, April 1st. Well, we don't meet on Tuesdays anyway, so this won't affect us directly, but Tuesday, April 1st is a special day here at GCC, and I just want to put it in your brains that there's something happening here. Anybody know? It's advising day. Tuesday, April 1st is advising day. So there are no day or evening classes on Tuesday, April 1st. That doesn't just mean like it's a day off and stay home. We want you to come in and we want you to participate in a lot of workshops that we have here on campus. I can give you details as I get them. But also we want you to come in and meet with your advisor and come out with a plan for what to take in the fall semester. And Tuesday, April 1st is the first day that you can register for classes for the fall. And for a few weeks here in the beginning of the registration period, it's called priority registration, which means current GCC students are the only ones allowed to register. But once that few weeks passes, then new GCC students will come onto campus and be allowed to register. And so the earlier you get in here, the more likely it is you'll be able to just take your pick of all the wide open classes. All right? So see if you can make an appointment to meet with your advisor on Tuesday. If you don't know who your advisor is, see me right after class and I will look it up for you. Any questions on that? Okay, so we're starting here again on page 14, right near in the middle, working with radicals. Just one little warning. Oh, so the tests are back out on the table. You can keep them now. So one warning, maybe more of an apology. There's going to be a lot of me talking today, and there's no group activity for this one. This particular class is just jam-packed with facts, and I apologize in advance. It's not going to be the most fun class for you guys of the semester. Unfortunately, I don't have anything better to offer you at the moment, so this is what we're stuck with. Okay, but we're going to try to skip around a little bit so that we don't get too caught up in all of these details. But let's just examine this symbol right here. Can somebody read that symbol aloud? Square root of 25 in this case, right? So what is the square root of 25? It's 5, because 5 times 5 gives you 25. Easy enough. Is there another number? So 5 times 5 gives you 25. Is there another number that I can multiply by itself, 2 copies of the same number, that also gives me 25? It's negative 5, right? Because if we do negative 5 times negative 5, we still get 25. So when I say find the square root of 25, it's really kind of misleading to say the square root, because really, how many square roots does 25 have? It really has 2. It has 5, which is the most common one that we'll talk about, but it also has negative 5. Now this is a point of confusion because this symbol right here, that square root of 25 symbol, means the positive one. Even though there are 2 valid answers to what are the square roots of 25, that symbol always means the positive one. And so that's underlined right here. That symbol means the positive square root. It's also called the principal square root. Not to take anything away from negative 5, which is a perfectly good answer, but that symbol only means the positive one. Okay, so in general, all positive numbers have how many square roots? They all have 2. One of them is what kind of a number, and the other is what kind of a number? Positive and negative. Okay, some square root vocabulary. Some words that we're going to mention right here: radicand, index, and radical sign. And this is the most general kind of thing I can write to capture all of the symbols you might see. So the first thing that I've got written here, x is called the radicand. So the thing inside the square root symbol or whatever symbol we have there is called the radicand. It's the thing inside. And then, where's my next word? Remember what you're trying to find. N is the index. We're going to talk about that. But anyway, sometimes we're going to see a little n up there. In most cases, that n is invisible because most of the radicals we deal with are square roots. But really, instead of just writing radical 25, if I want to be super precise, I should put a little tiny 2 up there to tell you I'm finding the square root, a number times itself, 2 copies of the number, as opposed to 3 numbers that multiply to give me 25, which we'll see soon enough. And then finally, that symbol right there is the radical sign. Okay, so just some vocabulary so you've seen it as you read. All right, so let's do a few easy examples here of square roots. So the question says, find the square roots, and I'm underlining that S to indicate that I'm asking for both square roots of each of these numbers. Okay, so first row, the number is 144. I want the positive square root, which we can symbolize with that radical sign with the 144. What is the positive square root of 144? It's 12. Now, if you get to bigger numbers or numbers that you just don't recognize, there is a handy reference sheet. It's the very first page of this packet. I think it's called like the perfect powers reference sheet or something like that. And it's got a list of all the perfect squares of the first few numbers and the perfect cubes of the first few numbers. Also, if you happen to be in this room, we do have some of these numbers on the walls. These yellow numbers, look at the bottom row. What are those? Those are perfect squares. So if I'm looking for the square root of 144, I just see if I can find 144 in this yellow list, and I look up and I say, oh, it's 12. And over here in green, the bottom numbers right here, anybody recognize? Those are the perfect cubes. So we'll see cube roots in a second, but if I said, for example, find the cube root of 3,375, what's the answer? It's 15. Right. So we've got squares and cubes on the wall if you happen to be in this room. Okay, that was the positive square root of 144. The negative square root of 144 is just negative 12. It's easy enough to write. But maybe more important than just writing that is to acknowledge that like that symbol is really the only way I can convey I want the negative version. Because if I just put this symbol, it is implied I'm asking you for the positive one. The only way we can get that negative one out is to throw an extra negative sign in the front. And I want to be really clear, this is not right. That symbol, square root of 144, is not equal to plus 12 or minus 12. It's not equal to 12 and negative 12. It is just 12. It's buried in the notation that we mean the positive one. But if I really want you to tell me both at one time, then I can ask you to calculate plus or minus square root of 144, in which case that plus or minus is just copied. And what's the value of that symbol, the square root of 144? It's plain old 12, okay? Okay, a couple more here. First one's a fraction. The square root of 16 over 25. Some of you will just know this right away, but if you don't know it right away, you're looking for some number times some other number to give me 16 over 25. Okay, the only way I'm going to get a fraction out is if there were fractions to start. So let me just go ahead and put some fraction lines in here. How does fraction multiplication work? Just straight across? So really, I'm looking for 2 numbers at the top that multiply and give me 16, but they have to be the same number. So what is it? All right, so those definitely are 4s, right? And on the bottom, 2 copies of 5 will get me the 25. Okay, so I think we've got our answer. What is the, I'll write the symbol here, square root of 16 over 25? That's 4/5. Not squared, just 4/5. This is something that it's, what's that? But we are finding like that symbol, that radical sign, is telling us to find the magic number, not to write it as squared, but to find the magic number that when you square it, you get 16 over 25. Okay, in the next column, if we just copy that square root thing, but insert a kind of artificial negative in the front, then what's the answer here? Negative 4/5. And if I really want to see both square roots of 16 over 25, what do I need to put in front of my radical sign? That plus and that minus. That's it. Okay. And then the last one is 7. What's the problem with this? It's not, I mean, it's not a perfect square. It's not in my list of yellow numbers up here. You're not going to find 7 in the bottom on yellow. There's no nice number that when you square it, you get 7. So if I ask for the positive square root, in some sense, like it's simplified as far as it'll go. You can't really do anything. If you really insist on doing something, you can type this into a calculator. Is the square root of 7 more or less than 5? It's definitely less, because 5 squared is 25, way bigger than 7. Is the square root of 7 more or less than 4? Less, because 4 squared is 16, which is still too big. More or less than 3? Less, because 3 squared is 9, but it shouldn't be that much less. More or less than 2? More, because 2 squared is 4, which is too small. So we know the answer to this thing, the decimal version of this thing, is somewhere between 2 and 3, probably closer to which one? Probably closer to 3, because that 7 is a little bit closer to 9. So, you know, I mean, you can play that game as long as you want. It's probably useful to just use the calculator to zip to a very accurate answer. Let's see, square root button. Oh, there it is, right there. Thank you. So I think, do I hit it that order? There it is, square root of 7. So we were right, between 2 and 3, a little bit closer to 3. So we'll say about 2.6. That's around 2.6. And the negative square root of 7 is around negative 2.6. And finally, plus or minus square root of 7 is around plus or minus 2.6. Okay, let's take a look at number 5. Have you guys seen this symbol before? I talked about how sometimes there's a little number up there. Have we seen this before? How do we read that in English? Cube root. That's the cube root of 64. How do we read this one? Yeah, this one is not really a word like cube. So let's go back and read this in an alternative way. Third root of 64, which means we can read this one as the fourth root of 64. So square root and cube root are kind of unusual in that they have special names. Normally you just read the number. Fourth root, third root. Nobody would say it this way, but I could say that's the second root of 7. Okay, can you guys fill in the 2 blanks right there with your neighbors real quick? Okay, so on the next page we can kind of verify our answers. We're going to write this in kind of a funny way, but it's got a point, so bear with me. We just decided the cube root of 64 is 4. And another way to write that equation is that the cube root of 4 cubed is 4, because 4 cubed is the same as 64, yes? So everything else in those equations is copied, and the 4 cubed is 64. And I can play the same game with the fourth root of 16, which we know is 2. Karen shared with us why, but you guys believe that 16 is exactly the same as 2 to the 4th, right? And basically that's why the answer was 2. And so if we're just looking for some kind of like a shortcut, if you see things written like they are on the right-hand side here, if you've got a fourth root and a fourth power, in a very real sense, they undo each other. They cancel each other, right? That fourth root and that fourth power, essentially, if you're just covering both up, you get the answer, yes? And the same thing up here, that cube root and the cubed power, the third power, if you cover them, you got the answer. So these two things are opposites of each other. They undo each other. And that's going to be useful for us. Okay, so let's come down here to this cube root of x cubed. Thinking of the idea that we just discovered, cube root and cube cancel. The answer to this problem is simply x, because the cube root and the cube cancel. They're opposites of each other. Same idea. Fourth root of x to the fourth is simply x. Okay, Now, I'm never going to give you ones as easy as those. So let's work on ones that are harder, which I will give you. Let's take a look at number 7. Number 7 asks us to find the cube root of 3 different things here. Cube root of x to the 6th, cube root of x to the 12th, cube root of x to the 21. Now, there are some different things that we might try to do here, but we're going to take this really slowly, and we're going to build up to a shortcut. So I don't want you guessing, because there's one right answer, and you might guess it, and you might guess other reasonable but wrong answers. So the basic idea here is that if you have a cube root and a cube, then they cancel, and the answer is whatever is left over inside, right? So what we're trying to build here is a cube root along with a cube. I don't like that 6th power there. I really want it to be a 3rd power. So I'm going to write this. If I could somehow fill in the blanks to make something equivalent to what I started with, then what would happen with the cube root and the 3rd power? They would cross off, and I would just get the thing in the parentheses. Okay, what I had inside of that radical was x to the 6th, so I better still get x to the 6th when I put something in here. All right, I'm going to put x, and I need to put a power right up here. Do you guys remember what happens to powers when they're right next to each other like that? They multiply. So what's the question mark supposed to be? If I need it to be 6, it's got to be a 2 in there. So does everybody buy that these are equal? I just wrote x to the 6th in a strange way. But I wrote it in a useful way, because we know that if we see a cube root of something cubed, the answer is just the something. So what's the answer to this one when I get rid of that radical sign? It's x squared. That's the answer to this one. And then we can do a really quick check. To say that the answer, forget this middle work in here, but let's just say we're checking to see if the cube root of x to the 6th is really x squared. Well, to say that that's the right answer means if I multiply x squared by itself 3 times, I should get the thing inside the radical. That's what the cube root means. And what do you do with powers when they look like that? You add them up. And what do we get when we add up all those powers? X to the 6th. Okay, so let's try this one here. Starting off with this basic shell, because I know I need to get a cube inside so that I can cancel. Sounds good. So we've got x to some power, and we know the powers multiply, and they got to give us 12. So x says 4. You guys buy it? That's how we're going to get a 12 in there. Yeah, and that's the shortcut. So let's get the answer here, and then we'll get to Zach's shortcut. What is this equal to? Is x to the 4th. For C, this should be the cube root of x to the 21. Okay, Zach's got a shortcut. Let's see if we buy it. Zach says, what does Zach say? So you're dividing these two in which order? So we take the 12, divide it by the 3. What does that give us? 4, which is the power, which is the bright power. Now let's check Zach's shortcut up here. So somebody not Zach, what is he suggesting we do with 3 and 6, Megan? 6 divided by 3 is 2. Is that the right power? Yeah, I'm feeling pretty good about Zach's shortcut. So that's it. So let's see if we can use Zach's idea to do something like a D, or skip C. Well, actually, let's just use Zach's shortcut and C. So don't say it out loud, but just write the final answer. Zach says we're taking one number and dividing it by another, and that gives us the power. Okay. Somebody we haven't heard from yet today, what are we dividing? 21 by 3, 7, so what's the answer? X to the 7. That's correct. Good. Okay, let's see if we can do this question mark business here. Still going to use Zach's idea that we're dividing. Here I'm trying to fill in the question mark as opposed to trying to find the answer. So what are we dividing with Zach's idea? So we're taking the question mark and we're dividing it by the 3. And what are we supposed to get as the answer? Supposed to get 8. That's really what this question is asking us to find. So can we look at that and find the question mark? What is it? 24? That's good. What you're multiplying is this by this to get that. That's not typically the way the questions will be asked, but if you do get this kind of a funny looking question, then yes, you're multiplying them. Yeah. Okay, so it says that in the exercises we just looked at, that all these guys, x to the 6, x to the 12, they're all examples of perfect cubes. They are perfectly cube rootable, if that makes sense. Because the variable, the exponent up there was always a multiple of 3, which was kind of convenient for us in these ones. So here's a question. Is 8, just plain 8, a perfect cube? If I asked you for the cube root of 8, would we get a very nice number or would we get some decimal? We get a very nice number. If you're not sure what it is, you can look on the green, you can look on your perfect powers reference. Hopefully for small numbers, you actually just start to get a feel for what the nice ones are. But this one is just plain old 2, right? So what about x to the 8th? Will we just get x to some nice old power up here, or is it going to be something that's kind of messy? What's Zach's idea? Divide what by what? 8 by 3. Does that go nicely? No. So unfortunately, this isn't a nice answer. That doesn't mean Zach's idea doesn't work. It does. His idea is sound. But just that x to the 8th, I would say, is not a perfect cube because it just doesn't have a really nice cube root. So the answer to this one is a yes. 8 is a perfect cube, but x to the 8th is not. And so what that means is that you have to avoid the temptation to somehow relate the cube root of 8, which is a very nice number, to this problem. When you see the cube root of x to the 8th, you're not thinking cube root of 8 at all. You're thinking division. That's what Zach says, right? So you got to be really clear the difference between finding the cube root of a plain old number versus finding the cube root of x to a number, because we do two very different things to the number. The 8 and the 8 we do very different things to. Okay, so skipping number 8, we'll just come down to the conclusion. It says in general, if we can, or we can eliminate the radical sign for expressions of the form this is just a generic looking radical here, as long as k is a multiple of n. K has to be a multiple of n. Just looking back up at the top, this example we did here with the a, b, and c. Is 6 a multiple of 3? Yeah, is 12 a multiple of 3? Yeah, is 21 a multiple of 3? That's why all of them worked, is because the power up there was a multiple of the index. Looking at this guy over here, a cube root of x to the 8, is 8 a multiple of 3? No, that's why that one didn't work, all right? So nice things happen as long as k is a multiple of n. Next page. Can you guys, with your neighbors, I think it'll take less than 30 seconds. Do number 10. If there's no number in front, it's equal to 2. Square root, you're looking for something multiplied by itself 2 times. So if there's no number in front, it's an implied 2. So if we want to use Zach's idea, we got to make sure we see that invisible 2. And then we can do our division. And what's the answer to this one? X to the 12, right? 24 divided by 2. Okay, so why do we leave it out? How come we don't just write 2 for square root every time we have to write that symbol? Because we're lazy. That's why. It's just convenient because square root is the most common root that we're going to deal with. it's convenient for us to just acknowledge that if there's nothing there, it's the common one, square root. Okay, let's take a look at 11. Square root of 9 times 4. All right, so first thing I want to do, no shortcuts here, just do the stuff inside the square root first. 9 times 4 is 36. Square root of 36 is 6. Is it plus or minus 6? Is it just 6? Just positive 6. Even though 36 has 2 square roots, that symbol, the radical sign, implies the positive one. So that's just 6. Okay, completely separate problem. Square root of 9 times square root of 4. What is the square root of 9? 3 times square root of 4 is 2, which is 6. Okay, there's something happening here that tells us that there are 2 different ways to get the same answer. It tells us that the square root of 9 times 4 is exactly the same as the square root of 9 times the square root of 4. That's a property. In fact, we see it right here. So if you have 2 things multiplied together under a radical sign, you are perfectly welcome to separate them as 2 different radicals and multiply them at the end. And the fact that that worked, it works in general. Let's try the same idea with division. So the square root of 9/4, I don't want you to think of this one as looking like part D right now. So don't do it like part D, but really ask yourself, okay, we're trying to multiply 2 numbers together and get 9/4, right? Just like we did before, that they both have to be fractions. And just like before, fraction multiplication goes straight across. So 2 copies of the same number upstairs are supposed to give 9. It's got to be 3. 2 copies downstairs to give me a 4. It's got to be 2. So what is the square root of 9/4? It's 3/2. Thinking of it this way. But then you can think of it this way, and then do the square roots separately and divide at the end. What's the square root of 9 on top? It's 3. On the bottom, it's 2. And lo and behold, we have another property of radicals. And that's this one over here. So if you have the square root of or any root of a fraction, you're perfectly welcome to separate that into 2 different roots and then divide them at the end. Okay, so that's going to help us simplify some stuff. What are we doing here? Okay, so let's do, so simplify the following. Each can be simplified so no radical remains. Kind of confused about why these first 3 are here. First 3 are pretty straightforward. Let's skip down to D. Yes. Okay, so this is I'm glad you asked that, because it's so easy to look at the square root of x to the 42 and think, okay, I got to find the square root of 42, and that isn't anything nice. This is your rule, Zach. This is not asking for the square root of 42, right? Yeah. So we'll bring Alex's idea. What's the invisible number? It's a 2. And then Zach's idea is 21. But this is why these kinds of problems get so confusing, is because you got to look at that 42 in exactly the right way. Sometimes I want you to say, oh, there's just no square root of 42. But other times I want you to realize, oh, it's just divide the 42 by the invisible 2. Okay, but let's come down here to D. How about the 4th root of 2? Is that a nice number? Is there a number that when you multiply by itself 4 times, you get 2? Yeah, but it's going to be some decimal, right? Like 1 point something. And the same thing for the 4th root of 8. And if you don't know your 4th roots, you have that perfect powers. I don't have any 4th powers on the wall here, but on the first page, you've got these perfect 4th powers. And 2 and 8 are not in that list. And how about x squared? Can we do something nice with x squared inside of a 4th root? If we do Zach's idea, do we get a nice number, like a whole number? 2 divided by 4, that's, I mean, it's a fraction, which is okay, but it's not a whole number like all the ones we did. And then over here, another 2 divided by 4. So at the moment, we are completely stuck on this. We can't do anything to them separately. But this very first property that we circled up here says, well, if you have separate ones with multiplication, only with multiplication and division, you can mush them together into one radical. So let's try that, because we've got nothing else that we can do. So rewriting this as one radical. It's still a fourth root. I have 2x squared, and I have 8x squared. And what's the magic symbol between? It's multiplication. They were multiplied before separately, and now they're multiplied together. And now that we have them inside of the radical, go ahead and do that multiplication. So smush those two things. And when we multiply those two things, we get what? 16 x to the 4. Okay, so this is fourth root 16x to the 4. One quick question. This 4, is it because we added the 2's or multiplied the 2's? It's added. We've got to be really careful, right? There's a multiplication sign. It feels like maybe multiply, but don't be tempted. It's addition. Okay, now the fourth root of 16x to the 4th. All right, I'm going to put in a step that I don't need you to put in, but I'll include it just to be really clear here. There's a multiplication there still. It's all multiplied. And I'm going to use that same property of multiplication going the other way. I have one radical with multiplication. I'm going to split it into two radicals. Fourth root of 16, fourth root of x to the 4th. What symbol is in between? Still multiplication. That's the same property, just going the other way. Okay, so the fourth root of 16 happens to be a nice number. It's okay if you don't know it at this stage. But at some point, I'd like you to know at least the first few nice fourth powers. But at this moment, if you don't know what the fourth root of 16 is, go to the very first page of your packet. Let's make sure we know how to use this chart. You're going to bring this chart with you to the next quests and the upcoming tests, so we want to know how to use it. So looking on that chart, we're looking for the fourth powers. Everybody see the fourth powers column? And you're looking for the number 16. So where in the chart do you see 16? It's on the line with the 2. So the fourth root of 16 is 2 times. Now the fourth root of x to the 4th, we actually could use Zach's idea here, but even more fundamental. We know that if we see fourth root and fourth power, they undo each other. So what's the answer to the fourth root of x to the 4th? X. So this one is just 2x. And so this is one kind of simplifying problem. We started off with two radicals at the start, multiplied together, and we couldn't do anything with them separately. So what did we do? We smushed them together. Why could we smush them together? Because there's a property that says multiplication works really well with radicals. And then we smushed them together, and all of a sudden these things that weren't nice, like the 2 and the 8 that we started with, became 16, which is nice. And then we separated, and we ended up with something nice at the end. Zach?
Why would it, or 16?
Yes? So you can't cancel the 2 4s here, because the only time we can cancel the 4s is if it looks like a bunch of stuff, all raised to the 4th. It's got to be one thing, all raised to the 4th. And yes, the 4s would cancel if the 16 weren't there, but you are kind of selectively putting that fourth root with the x to the 4th, but you're ignoring the fact that the 16 is there. Okay. All right, good. How about part E? Cube root of 8y to the 10, cube root of y to the 4. Can we use Zach's trick up here with the 10 and the 3? We get a nice number when we do his division? No. How about on the bottom with the 4 and the 3? No. So what do you think we're going to do because they're not nice separately? We're going to put them together. All right, let's use this quotient rule. Okay, so equals cube root. Put both of them together under the same radical, 8y to the 10 over y to the 4. Again, this is only okay because we had division. Notice that we have not seen a radical problem here with what two other operations? Addition and subtraction. They're coming on the next page, but to be clear, these are only multiplications and divisions where nice things are happening. Okay, cube root. Our job is to clean up this thing on the inside before we deal with the cube root at the end. Got to be really careful. We've got lots of laws of exponents. What are we doing with these powers? Subtracting them. So the 8 is staying right where it is. Y to the 6th. Do I need to have a denominator? No, the y to the 4th canceled completely. Abby, is that all right? That's okay? Okay. All right, again, I'm going to include a step I don't need you to include. You are welcome to just look at this and deal with the 8 and the y to the 6 separately in your head, but I'm just going to write it out in all the gory detail. That really I'm thinking about separating these guys again, which is okay because it's a multiplication. And once they're separated, I realize I have two very nice things I can handle. Cube root of 8 is 2. Zach's rule says y to the 2nd power, right? 6 divided by 3. Ooh. Yes, this only works when the index is the same. Good point. Yeah, I didn't really highlight that in the rules, but the ends have to be exactly the same all the way through. Okay. So really the most common way to get this wrong is to kind of say, all right, I know Zach says we get to divide the 6 by the 3 and say, all right, I get y squared, but then to not really recognize what to do with the 8. That there's still a cube root of 8 waiting to be done because in my mind they're separate. And it's also really easy to say, okay, I'm taking the 6 and dividing it by the 3, so I should take the 8 and divide it by the 3. And you just end up, you know, like merging together these two things that are really separate rules. Okay, let's take a look at f. F has 3 different square roots. Are any of those 3 nice? None of them are nice. So better do something to hope that something gets nice. What can you do when you have one number on the outside of 2 with a subtraction? The 3 is not, wait, say it again. You want to make the 3 the index? You can't change the index. There's nothing we can do to change the index. These are square roots through and through. Yeah, like if I just gave you something like this, 5x minus 2, what could you do to that? You could distribute, right? Well, that's exactly the same pattern as what we're looking at here. So the only thing we can do at this moment is distribute. It was half of a lobster claw if you took 095 with Sandy or myself. So root 3 times root 12. That's multiplying the root 3 times the first guy. What's the next symbol? Before the 48 is a minus, right? Copying that subtraction. And then the root 3 comes in and multiplies by the root 48. Now, admittedly, this doesn't look promising. In fact, it looks worse, right? I mean, it's bigger than it was before. But one thing we know we're allowed to do when we see multiplication with 2 radicals is what? We can mush them together. So this is really the same as root 3 times 12 minus. This is really the same as root 3 times 48. Still persevering. Nothing nice has happened yet. 3 times 12 is 36. Aha, the first nice thing. Okay. Now we have something we can simplify. Let's see, 120, is that 144? Aha, something else nice. So this is really 6 minus 12, negative 6. Okay, so of course this problem is contrived to take messy looking things and make them nice at the end. If you just pick random messy things, they're going to be messy at the end. I picked something here where everything would work out nicely. But the point of this problem is to get practice using our new property here. Okay, next page. All right, so let's try some of these. These are quite common in terms of test questions. Square root of 18. This is going to be something new for us. Is the square root of 18 a nice number? No, it's like, 4 point something, but it's not a nice number. But there is something nice that we can do with it. And in fact, we're essentially saying, what does it mean to simplify a square root when it's not a nice number? So here's what we're going to do. We're going to take that 18 and we're going to write it as a product of two numbers. 18 is really something times something. 9 times 2. Is 18 the product of two other numbers? Something times something. Could do 18 times 1 and one more. 6 times 3. We have 3 different ways to break up 18. Turns out one of them is useful and the other 2 are not. So let's do this in detail. We know that we can take a product and separate it. So this is really square root of 9 times square root of 2. And down here, this is square root of 18 times square root of 1, square root of 6 times square root of 3. Okay, let's look at the bottom row. Is square root of 6 anything nice? No. Square root of 3? No. So there's nothing I can do with this. I guess I could break 6 down into 2 times 3, but there's nothing good in there. So it's accurate, but it's not helpful. Square root of 18 and square root of 1. Well, square root of 1 is nice. What's the square root of 1? Just 1. So this is just saying it's 1 times the square root of 18, which is true, but it's exactly what we started with. So that one isn't going to get us any place. Square root of 9. Nice. It's just 3. So this is the winner. So this is really equal to 3, and then I'm going to copy this other guy, and we're done. You can't reduce the number 2 any further into something square root and something else square root. But we took 18. 18 wasn't nice, but 18 had a nice number hidden inside. 18 has a 9 hidden inside. And 9 is something we can handle with that square root. So we pull the 9 out, separate it, write that square root of 9 as a 3, and we're done. Just in case you're not convinced, let's do this actually on this guy instead. So if I type in the square root of 18, again, we were looking for 4 point something. There it is. If I type in 3 times the square root of 2, 3 times the square root of 2, get that. So they're exactly the same, 2 different ways to write the same number, just like, for example, 2/6 is exactly the same as 1/3. Of these two numbers, these two fractions, which one am I going to give full credit for on a test? It's third. I'm never going to give you full credit for 2/6 because you know it's not simplified. It's not reduced. I'm now telling you what it means to reduce a radical. It means you got to take out any factors that are nice. 18, you have to pull out that 9. You cannot leave square root of 18 in an answer, just like you can't leave 2/6. Okay, so let's do something else. Let's try let's try part C right now, actually. Yeah, let's jump to that one. Okay, cube root of 32y to the 17. 32y to the 17. Okay, is 32 nice? Inside of a cube root, it's not. It actually is nice inside of a different root. Again, can you look on that first page? Just want to make sure we're really good at using this reference sheet. Looking at the third powers, do you see 32 in the list? No, not in the third powers. So we can't do anything with it here. But do you see 32 in any other column? It's the fifth. So if this were a fifth root of 32, what would the answer be? Just 2. So it's not enough, like I can't just say is 32 a nice number. I have to say is 32 inside of a cube root a nice number, because it makes a difference which column you're in. Okay, so 32 is not a nice number in that cube root column. Now, there are a lot of different ways to factor that number 32. I'm going to write them, but please don't copy them because we're only going to want the one that works. But for example, 32 is really 2 times 16. 32 is also 4 times 8, right? Anything else? think that's it. Okay, so the question is, which one of these is going to help us? Again, you're really greedily just looking at that cubed column, and you're looking to see if any of these numbers are in there. So those are all the choices. Do you see any of these numbers in that list? In the cubed list? What number is in the list? Yeah. The perfect cubes. One of these numbers is there. It's the 8. 8 is in that list. So in terms of the factoring we want, it's not just any old factoring. It's only the ones that's going to find you something that's in the list. Okay, but writing down all the factors of a number can be really time consuming, especially if it's a big number with a lot of factors. Like if this was 144, there might be like a dozen different ways to factor 144. So instead of just listing them all and then trying to find something on the sheet that's in this massive list of numbers, here's the better way. What you want to do is say, okay, this is a cube root problem. So we're going to look at the cubed column. What's the first number in that cubed column? It's 1. Okay, 1 is always a factor, but 1 is never going to get you any place. So you look at the next number. The next number is 8. And you ask yourself this very pointed question. Does 8 go into 32? Yes, it does. So that's our winner, right? If 8 didn't go into 32, I'd look at the next. So I'll just write the question. Does 8 go into 32? The answer here is yes, so we've got our winner. But if the answer were no, I would look at the next number in my list. What's the next number in that cubes list? Is 27, and I would say, does 27 go into 32? Say no, and then the rest of the numbers are already bigger than 32. So we would just keep going until the numbers were too big, and we stop. So it's not just a factor willy-nilly and cross your fingers. It's a use that list and find the number that's going to work. Okay, so let's see if we can do this one. Cube root of. Okay, we said that 8 was a good thing. So we're going to take 32 and factor it as 8 times something. What's the something to give you the 32? 4 times. Okay, now I've got that y to the 17. Again, Zach's rule says do what with these y's, or with the numbers here? What am I doing with the 17 and the 3? Just divide. Does it go nicely? No. So what we're going to do is we're going to split these y's into 2 separate pieces. Just like we factored the 32 into 2 different things, the 8 was nice and then the 4 was just left over. You're going to take those 17 y's that you have to play with and you're going to split them up intelligently. We want to be able to use Zach's rule. Zach's rule says take 17 divided by 3. Shoot, it doesn't go in evenly. Okay, well, one way, don't write this, but one way to split up my 17 different y's is to say, okay, I could put 16 of them and 1 of them. I still have 17, right? Let's try Zach's rule on the 16 and the 3. Is that any better? No. So this wasn't a good way to split. So I could have tried and said, okay, what about 15 and then how many y's left over here? 2. So let's try Zach's rules right here. 15 and 3, does that work? Yeah. I got 15 and divide it by 3. That's Zach's rule. Does 15 divided by 3 go nicely? It does. This is our winner. What is it about 15 that makes this a good choice? It's the largest amount we could take out of the 17. You have only 17 to play with. You want to pick as many as you can, such that what was true? Why is 15 nice? Because it's divisible by 3, right? We want to be able to use Zach's rule and get a nice number. Zach says you take the power, and you divide it by this index. 17 divided by 3, not nice. 16 divided by 3, not nice. 15 divided by 3, that's the winner, okay? This is tricky, guys. I know it is. The second one is a 2. Yeah, it's a 15 and a 2. Okay, let me let's pause on that one. We'll finish that one in just a minute, but let me just try a different one. Let's go with this. Let's make this a 7th root, and I'll make it x to the let's say 41. 7th root x to the 41. So this is Zach's rule right here. What are we doing with 41 and 7? We will split. But first attempt is to divide. Does it work? 41 divided by 7, nothing nice. So what we need to do is take those 41 x's and split them up into 2 pieces. Okay, we're going to split those 41 x's into 2 pieces. The first choice, don't copy this, but the first choice is to say, okay, what if I put 40 of the x's over there and just 1 solitary x over here? And then we try Zach's thing again, 40 and 7. Does that go in evenly? No. So this wasn't the right way to split. So then we try, okay, what about 39 and then 2 x's left over? Does 7 go into 39? No. And so you don't need to go one at a time once you understand what the goal is. The goal is to put a number in that first box that's divisible by 7. What's the first number we're going to get to that will be divisible by 7? It's 35. Now we'll fill in the other box. We had 41 x's. 35 of them are already accounted for. 6 are left over here. So what made these 2 numbers nice is that the one was divisible by the other. 35 was divisible by 7. Why did we end up with a 15 over here? Because we got something that was finally divisible by 3. This is what made Zach's rule tick, is that something was evenly divisible by that index. So you take all the x's you have and you split them apart, but you got to split them apart in exactly the right way. Okay, let's come back here to this cube root one and we're going to finish it. Okay, this guy equals. All right, I'm going to split this up into 2 radicals. Okay, the first radical is going to be all the nice stuff. The 8 and the 4, which one was the nice one? It was the 8. The reason we split it this way was because 8 was in our list. So the 8 is going into the good radical, and the 4 is going into the whatever's left over radical. Y to the 15 and y squared. Only one of them is nice. Which one was the nice one? It was the 15. We built 15 because it was going to be perfectly divisible by 3. So we'll put y to the 15th over in the party radical, and then y squared home alone. So we split it up so that we got all the nice stuff in the one and everything left over in the other. Okay, and then we're ready for the last step. Cube root of 8, 2. Cube root of y to the 15 is y to the 5th. There's a hidden symbol in between. What is it? Multiply. You don't need to include it, but just highlighting. And then I'm going to copy the other one, the radical that was full of the leftovers. There's nothing more that we can do with that one. That's our answer. We squeezed everything good that we could out of the beginning radical. That 32y to the 17, we pulled all the good stuff out to the front, brought it outside of the radical, and then we've got this leftover stuff that there's nowhere to go. Remember I had said 2 classes ago that the exponents part is where a lot of students struggle. So this is in there with the exponents. We'll see. I mean, we see exponents here already. So this is what I'm talking about. Is that, like, I know this is hard, and I have seen students take all these rules and just like throw them all in a hat and like randomly pick one and apply it to a problem. And like, you just got to really take your time. Be patient with yourself. This is a complicated process here. I recognize that. Okay, let's go back up to part B. Hang in there. We've got 12 minutes left. You guys are going like champs right now. Let's go back up to part B. Square root of x to the 13. Alex has told us there's an invisible what? 2. Zach has told us we do what to those numbers? Divide. Okay, it doesn't work nicely. So this is the idea, again, where we got to split it. So We are splitting. I'll copy the 2 there. I really think it's a good idea. If you're going to split some x's up, I think it's a really good idea to just put x with a couple of blanks up there. And then it's just a game where we fill in those blank boxes. Okay, so what's the first way we could split up 13 x's? How many in the first one? We could do 6 in the first one, but let's do the biggest number we could in the first one. You have 13 of them, 12 and 1, right? That's the most greedy way we could split them up, is to put 12 of them in the first one and just the 1 left over in the second one. And that's how I always start as I'm splitting. I just put 1 over on the side and then everything else. Is this nice? Is the square root of x to the 12 something good? Zach says it is, because what are we supposed to do with the 2 and the 12? Is we divide them. And it worked. Why couldn't we just do that in the beginning with 13 and 2? It doesn't go in. Right? 2 doesn't go into 13, so we can't just divide them. But 2 goes into 12, so we win. I mean, like, we have split it up in a good way. So I'll actually just write out the split here. So this is the square root of x to the 12 times the square root of x to the first and then again using Zach's rule, what am I doing with 2 and 12? Divide, so we go x to the 6th times, and then I'm just going to copy this square root of x without all the other numbers. And that's it. Questions on that one? Victor. We have a what? Yes. What you have to copy is whatever that guy is. That one gets copied. So here there was a single cube root, and then it became 2 cube roots, but it gets copied however many times you split it. Yes. Really, the only simplifying happened right here. We got something we could handle there, and we turned that into x to the 6th. That was really the only simplifying part. Okay. All right, let's try one with division. Okay, 32r to the 49 on top. It's in a cube root. Downstairs is 4r to the 8. Okay, there are different choices here. One option would be to try to take the top thing and split it up into some nice stuff and then whatever's left over, and then do the same thing downstairs. Nice stuff and whatever's left over. I do not think that's the best option. I think the best thing is to first smush these together into one fraction, which we're allowed to do because it's division. So my strong recommendation is that you first combine these as one fraction. So everybody buys that's legal, right? That's our division rule for radicals. And the reason I like to do that is because sometimes things just cancel. And if stuff cancels, then it's less I have to deal with. So what happens with the 32 and the 4? Turns into 8, which is really lovely because 8 is a nice number inside of a cube root. But 32 wasn't, and 4 wasn't. But if I just smush them together and let the smoke clear, I get something nice. Doesn't always work, but it's worth a shot. What am I doing with these powers to simplify? Subtract. 49 minus 8, r to the 41. And I like this one so much better than the first one because I don't have a fraction anymore. I just have one radical to deal with instead of 2. So strong recommendation, if you have division, try to smush them together first. Maybe some stuff will go away and make life easier. Now we got to separate. Okay, is 8 a nice number, or does it need to be split up? 8's nice. 8 is in our perfect cubes list, so 8 is fine. How about r to the 41 as a perfect cube? Is that nice or not nice? Said another way, does 3 go evenly into 41? No, unfortunately it doesn't. So we will have to split up that 41. Kind of running out of space here. So let's split. This guy equals cube root, copying the 8, and then I'm going to follow my own advice where I put R with a couple of boxes. All right, gang, here's the game. We have 41 R's to play with. 41 was not nice because it wasn't divisible by 3. So you split. Let's split one of those R's off. So how many R's would be in the front? That will be the winner, yes, but let's just split one of them off first. If we had 40 and 1, that's the first thing I would try. And I would ask myself, is 40 R's a nice thing? Does 3 go into 40? No. So I'm not going to split it off as 40 and 1. What's the next number we could try? 39 and 2. Is 39 a nice number up there? Does 3 go into 39? It does. So that's the winner. Right? So we're going to split off 39 R's and then have 2 left over. 39 and 2. Okay, I'm not going to split this up. I really don't have room to do it, so we'll just deal with the nice stuff, pull it right outside now. Cube root of 8 is 2. R to the 39, cube root of that, R to the 13. Cube root of R squared, it's not nice. It stays. It is quite common to still have a radical left over when you're simplifying a radical. That's 2R to the 13 times the cube root of R squared. It's tough. Questions on these? Okay, let's move on. Changing gears just slightly. We have done lots of stuff today with square roots of products and square roots of quotients. Multiplication and division work really nicely with radicals. But let's see if there's anything nice going on with addition and subtraction, which we have avoided completely so far today. So let's try this first one here. Square root of 9 plus the square root of 4 is really 3 plus 2, which is 5. Great. Over here, square root of 9 plus 4. It is very tempting to look at this and see the first problem. It's really tempting to look at that square root and think that we can just put it over both numbers and say, oh, it's really just 3 plus 2. But forget that idea for a moment. Just do the addition first. That's the square root of 13. Is the square root of 13 5? No, it's 3 point something. Okay, so this is enough. Are we allowed to see this square root of 9 plus 4 as, in some sense, going over both of the numbers? No, it just plain doesn't work. If it were addition, sorry, if it were multiplication, it works. We saw that it worked. But addition, it just doesn't work. Same thing with subtraction. Nothing good for addition or subtraction. So radicals of these forms, square root of x plus y, square root of x minus y, any addition or subtraction cannot be simplified. I say again, cannot be simplified. All the ones that we worked through today to simplify were products or quotients. You can double check if you don't believe me. We saw not a single addition sign or subtraction sign inside of a radical. Okay, so in particular, this square root of a squared plus b squared, it is tempting to think maybe that's just a plus b, but it's not. And that line going right through the equal sign is not emphatic enough to indicate how wrong this is. So just like really, like please don't do that. It just doesn't work. It feels like it should. Like it's defendable. It seems reasonable that you could just take that square root and split it up. It just doesn't work. Okay, that said, there is something we can do with addition and subtraction of radicals. An example down here in 17a. It says add the like radicals. 5 radical 7 plus 3 radical 7. Okay, forget the word like for a second, but suppose that I just change this radical 7 to an x in my mind, which means this radical 7 is also an x. So this problem is really asking me to take 5x and add it to 3x, which I can do perfectly well and get 8x. So this is 8, but don't put x. What is x really? Radical 7. That's it. So we can add these two radicals because they're exactly the same. Because they're exactly the same 7. And more than that, what else is exactly the same for those two radicals? Is they're both square roots, right? If one of them was square root of 7 and the other one was a cube root of 7, can't do anything with it. This only works because they are exactly the same. So that's what it means to be like radicals. Go ahead and write your answer to part B here. 8 radical 10 minus 12 radical 10. So what do we get? Negative 4 radical 10. Done. What do we think about this one here in C? Radical 12 minus 2 radical 75 plus 7 radical 27. Are any of them like radicals? They aren't. None of them are exactly the same. 12 is not the same as 75, is not the same as 27. So on the surface, it seems like there's nothing that we can do with this one. But it turns out we can. Because, we'll pause here, we'll stop here in just a moment. But that square root of 12 is exactly the same as square root of 4 times 3. And we know that radicals work really nicely with multiplication. So that square root of 4 I can picture as being separate and take it out. Square root of 4, square root of 3. And the square root of 4 is a nice number. It's 2. So that square root of 12 is exactly the same as 2 square root of 3. This is something that we have done today. Where to go? Didn't we do a square root of 18 somewhere? Right up there. We did the square root of 18. Cleaned it up as a 3 radical 2. So we're going to end here and we'll pick up on this one next time. But that square root of 12 is really a square root of 3 in disguise. And potentially, maybe the other radicals are also some other things in disguise. We will handle that. We will do this one. First thing we'll do next time. Okay, real quick, guys. In terms of homework, there's still a little bit left in this class, and I recognize that this class is really longer than a full class, and the next one is shorter. So we're going to finish this next time. In terms of homework, it's here. If you have a good handle on what we did today, you'll be able to do most of the stuff. There'll be a couple of things that you haven't seen because we didn't quite get there. I'm going to say you can do all of it if you want, or you can do none of it. I'd encourage you to do at least some of it because there will be another homework assignment next time. But this isn't technically due next time because we didn't quite finish, all right? Okay, we'll see you guys on Friday. 14.